So, in the last class, if you remember, we completed the BGAM method. In BGAM method, basically we are handling the greater than equals type constraints by the introduction of surplus variable and artificial variable, where in the cost coefficient, again if you remember, then in the cost coefficient what we were doing for the artificial variable, we were attaching one high penalty, that is minus m, and we have made one assumption that value of m is sufficiently large. Now, sufficiently large means we wanted to say that m minus some quantity, if we subtract from m, if we subtract some quantity, then m will always be greater than that quantity. But whenever we are implementing it in computer, because when number of variables, number of constants are much more, then manually we can't do it. So, if we can't do it manually, we have to write down programs for implementation of this. There it becomes a issue, what should be the possible value of this capital M. So, that is one problem of implementation of the BGAM method. To overcome that particular method, we now today discuss another method which we call as two-phase method. Basically, in two-phase method, we are trying to do one thing, that is, we will try to remove the artificial variable from the basis, that is one type, and if we have the redundant constants, we will come to that. There are certain effects if we have redundant constants, that is also being taken care of in two-phase method. So, basically it has two particular steps. One step is, if you have redundant constants, then how to handle the redundant constants, because it leads to certain thing, and the other one is to handle the artificial variables. Here you will find that the artificial variables are not associated with some very large coefficient value, but a negative only one value, that is minus 1 will be the coefficient of the artificial variable, and that is also not in the original objective function. Basically, we are doing it in two phases. In the first phase, we are trying to find out the initial basic feasible solution, and by doing this, we are creating one auxiliary objective function by considering all the elements, or for all the variables of the auxiliary objective function as 0, except the artificial variables, and for the artificial variables we have taken the coefficient as minus 1. Then we are running the first phase of the two phase method using the normal simplex approach, whatever we learned earlier. Then once zj minus cj greater than equals 0 and it satisfies some other criteria, then we go to the phase 2 for the optimal solution of the initial basic feasible solution, whatever we have derived from phase 1. Now, let us see what are the phase 1 and phase 2 of the system. So, we are now trying to do the two phase method. In two phase method, as I told, the first phase is phase 1. Here you see we have written it pointwise, what steps you have to follow. Convert each of the constraints into equality constraints using slack, surplus and artificial variables, and write the LPP in standard format. Please note this one, the step 1 already we have done for simplex approach or for the BGAM approach. That is, you have been given the LPP in canonical form. From the canonical form, you are converting the LPP into the standard form by converting each constraint into equality constraint with the help of slack variable, surplus variable and artificial variables. Step 2 is, we assume a new auxiliary objective function. Here we create this auxiliary objective function, if you see, it is maximize z star equals, as I told, for all the variables 0 into x1, 0 into x2, like this way, 0 into xn, minus 1 into x a1 minus 1 into x a2 minus 1 into x an, where minus 1 is the price added for each of the artificial variables x1, x2, xm. So, please note that if I have m artificial variables x a1, x a2, x am, then in the auxiliary objective function we are adding a price minus 1 by writing minus 1 into x a1 minus 1 into x a2, like this way, minus 1 into x am, and 0 price is assigned to each of the variables x1, x2, xn. This x1, x2, xn contains the decision variables as well as slack and surplus variables. So, please note this one. If I have the decision variables and slack and surplus variables as n variables, then those n variables x1, x2, xn, the coefficients in the auxiliary objective function we are giving as 0. So, the new objective function we have created, where all the variables except the artificial variables we are giving the coefficient we are assigning as 0, whereas for artificial variables we are assigning the value as minus 1. So, maximum value of z star, if you see, it will be 0 whenever value of all artificial variables will be 0, which actually we want, that we want to make all artificial variables as 0. So, whenever maximum of z star equals 0, all the artificial variables will be 0, or it may happen that value of maximum of z star is less than 0. This will be possible only when if at least one artificial variable is positive. So, if at least one artificial variable value is positive, then maximum value of z star will be less than 0 from this z star. So, please note these two things. Step 3 is apply the simplex algorithm to solve the problem. That is, the simplex algorithm, whatever we have used earlier classes, you use that particular algorithm to solve this problem. Maximize z star equals this new auxiliary objective function subject to the original constraints. Now, certain cases may arise. What are the cases? Suppose your zj minus cj, you know it, zj minus cj is the result of the reduced cost value. So, if zj minus cj is greater than equals 0, you got after some iterations on the simplex table at the end of phase 1. So, whenever zj minus cj will be greater than equals 0, then value of z star can be 0 or it may be less than 0. Now, what does it mean? Now, whenever maximum of z star equals 0, it means that all artificial variables may disappear from basis. All artificial variables may disappear from basis, because it will be 0 only when your artificial value of the artificial variables are 0. So, from this maximum of z star equals this objective function, it is clear. And in that case, if the value of all artificial variables disappear from the basis, then we get a basic feasible solution. The next case may come on z star equals 0. One or more artificial variable may appear in the basis with 0 variable, because in the first case we have told z star equals 0 means all value of the all artificial variables must be 0, then only z star will be 0. But your value of all artificial variables are 0, but one artificial variable still is there in the basis, that is still it is a basis variable. That means we have a basic feasible solution of the problem, but there may have redundancy on the original constraint equations. That means whatever constraints we have used, there may have redundant constraints, means if we would not have written one constant, then also my problem would not have affected. So, please note this one, that if maximum value of z star is 0 and if one or more artificial variable appear in the basis with 0 value, appear in the basis or it becomes basic variable, in that case you will obtain the basic feasible solution, but there may have redundancy in the constraints, and redundancy causes certain other problems which we will discuss again later stage. The third case, that is C part, will be maximize z star less than 0. So, whenever z star is less than 0, that means all the artificial value of all the artificial variables are not 0. Some or one or more artificial variable will appear in the final basis with the positive value. So, please note this one or more artificial variable must appear in the final basis with positive value if value of maximum value of z star is less than 0, and in that case there will be no basic feasible solution of the original problem. So, that means from phase 1 itself we can conclude that there is no solution of the original problem. I do not have to go for the iterative steps in the phase 2 for getting the optimal solution. So, basically we are reducing here the number of iterative steps before concluding that the original problem has no solution. So, note these things. At the end of phase 1, maximum value of z star can be 0, it may be less than 0. So, z star equals 0, it has two implications. One implication is all the artificial variables will disappear from the basis and we will get the optimal solution if it is there. And it may happen that although z star is 0, but one or more variable are appearing in the basis, one or more artificial variable is appearing on the basis with 0 value. This means that some redundancy is there in your constraints, whereas z star less than 0 means there is no solution of the original problem, because z star less than 0 means one or more variables will appear in the basis or final basis where the value of that artificial variable is positive value, that is greater than 0. Now, in phase 2 what we do? When iteration of phase 1 and phase 2 ends, then either 4a or 4b will come, because 4c will not come. We will not, whenever we know that original problem has no solution, we will not go for phase 2. So, for phase 1 ends, we will go for, there will be either two cases and 4a or 4b, and in that case only we will go for phase 2 to obtain the optimum value of the objective function of the original problem. Now, you assign actual coefficients of the variables, including slack and surplus variables and 0 coefficient value to artificial variables present in the basis of the last table of phase 1. So, as I have told at the beginning itself, at first we have created one auxiliary objective function, where the coefficients of the variables were not same of the original problem, but we assign 0 values to all decision variables and slack and surplus variables, and we have assigned -1 coefficient to the artificial variables. But now whenever we are going to the phase 2, we are assigning actual coefficient values of the variables for all the decision variables, slack variables and surplus variable. And please note it, if any artificial variable is present, then we are assigning 0 value as a coefficient for that artificial variable. That means, in this phase, two phase method, we are very clearly telling what will be the coefficient of artificial variable in the objective function, which we defined as m, a very large number in the big M method, which is the basic difference between these two. Next is also remove the artificial variables which are not present in the basis of the last table of phase 1. That means, columns of the artificial variables will be removed which are not present in the basis. So, any artificial variable will be present in the table only if it is present in the basis of the last simplex table of phase 1. And then you apply the simplex algorithm as usual to obtain the optimum solution. In case of 4b, that is, whenever your you may have some your 4b says that one or more artificial variables may appear in the basis with 0 values. So, in that case, add one or more artificial variables appear in the 0 value. We should take care so that these artificial variables may never become positive in any iteration, or in other sense their values should remain 0 always. They should not take any positive value, that we should take care. So, this is the basic idea of the two phase method. In phase 1, you are creating one auxiliary function by giving the 0 value to all the variables, including decision variables, slack variables and surplus variables, and -1 as a coefficient for the artificial variables, and you will stop whenever your zj minus cj is greater than equals 0. So, when zj minus cj greater than equals 0, that means value of z star will be either 0 or it will be less than 0, which we have discussed. 3 different cases, 4a, 4b and 4c. In the case of 4c, there will be no solution, since artificial variable is present in the basis with the positive solution. So, you can obtain the basic feasible solution for the case of 4a and 4b only. In phase 2, you are actually assigning the original coefficients of the decision variables and artificial variables and decision variables, slack variables and surplus variables. Whereas, if artificial variable is present in the basis, then we are assigning 0 coefficient to that particular artificial variable. Now, let us explain this algorithm by some examples. Let us take some cases. Let us take the first example. I want to maximize 2x1 plus x2 plus 3x3 subject to x1 plus x2 plus 2x3 less than equals 5 and 2x1 plus 3x2 plus 4x3 which is equals to 3, and of course, you have the non-negativity restriction, that is x1, x2, x3 greater than equals 0. So, first thing what I will do, I will write it in the standard form. I will write this one in the standard form. In standard form, it will be maximize z, I am not discussing this, equals subject to x1 plus x2 plus 2x3 plus it is less than equals. So, you will add one slack variable here and this is equals 5 whereas 2x1 plus 3x2 plus 4x3 plus 0 into x4. To get the initial basic feasible solution, as we have discussed earlier, you have to add one artificial variable over here. So, plus x5, this is equals to 12, and here it is plus 0 into x5. So, that you are writing your problem as 2x1 plus x2 plus 3x3 plus 0 into x4 plus 0 into x5. Please note that here your x5 is the artificial variable just to get the initial basic solution for this particular set of constraint. And although x5 is the artificial variable, but you have added one 0 coefficient only. This is the difference, first difference between the big M method and the your two phase method, because in big M method you added a penalty of minus m with the artificial variable x5. Now, this is your problem where your xi is greater than equals 0, I equals 1 to 5. So, your problem, standard problem is this. From here, now you will create one auxiliary objective function. So, your auxiliary objective function will be your auxiliary objective function. Now, you are writing, as we have told, your auxiliary objective function will be say z a or z star, whatever name you can give. Here you have only one artificial variable x5, you have three decision variables x1, x2, x3 and one slack variable x4. So, according to the algorithm, all the decision variable and the slack variable will be associated with the 0 coefficient, whereas the artificial variable will be associated with the coefficient minus 1. That is z a equals, you can write down 0 into x1 plus 0 into x2 plus 0 into x3 plus 0 into x4 plus minus 1 will be added with the as a coefficient of the artificial variable. So, now your new auxiliary objective function is maximize z a equals 0 into x1, 0 into x2, actually this is these are into x3 and minus 1 into x5. So, your problem is maximize z a subject to these two given constants using the simplex algorithm. So, what will be your initial solutions? Your initial solutions will be here variables are x4 and x5, and the variables from here you can obtain x4 equals 5 and x5 will be equals to 12. This is the initial basis in this case, because I have to make all other variables as 0. So, you write down here x5 and x4. So, that this will be also a5 and a4. Value of Cj is not the original one, but for the new objective function. New objective means auxiliary objective function. So, it will be for all variables it will be 0 and minus 1 only for the this objective function. So, Cb here it is minus 1 and 0, your b value is 12 and 5. So, corresponding to x5 you are writing this one, that is 2, 3, 4, 0, 1, and corresponding to x4 it is first one. So, it will be 1, 1, 2, 1, 0, 1, 1, 2, 1, 0. So, once you are obtaining this, you can calculate the value of Zj minus Cj as usual, and you can check whether Zj minus Cj greater than equals 0 or not, and you will repeat the process. So, Zj minus Cj value if you calculate, then CBXB minus Cj. So, it is equals to minus 2, I am not explaining, minus 4, 0 and 0. So, the most negative is this one, that is this column. So, your entering vector will be x 3. So, your entering vector is x 3. So, you have to calculate the ratio, that is b by x b. So, ratio in this case 12 by 4, that is 3, and in this case 5 divided by 2, that is 2.5. So, your outgoing vector is x 4. In this case, your outgoing vector is this one, that is x 4. So, in this particular iteration, your entering vector will be x 3 and it will be replaced by the outgoing vector x 4, and your pivot element is the intersection of these two, row and column. So, this one, that means I have to make this column as 1 and this column as all other columns as 0, all other elements of this column as 0 as usual. So, the next table whatever you will obtain is this one, 0 0 0 0 minus 1, and here it will come as x 5 and your entering vector is x 3. So, x 4 will be replaced by this. So, that it is a 3 and a 4. Your CB values will be minus 1 0. So, I am directly writing this. I have to make this as 1 and this as 0. Accordingly, I have to perform operations on the row. So, it will be 5 by 2, half half, 1 half, 0, and the other row will become 2 0, 1 0, 1 0 minus 2 and 1, and your Zj minus Cj becomes, if I calculate, it will be 0 minus 1 0 2 0. So, if you see here, still your Zj minus Cj is not greater than equals 0, we have a negative. So, this will be x 2 will be entering. So, now I calculate the ratio 2 by 1 2 and 5 divided by 1 by 2. So, it will be 5. So, outgoing vector will be x 5 and your pivot element will be 1. So, this is already 1, I have to make it 0. So, in the basis now x 3 will be replaced by x 2. So, it will be now x 2 x 3. So, 0 0 0 0 minus 1, your b is a 2 a 3, your CB will be in that case 0 0, x 2 x 3 is 0. So, these values will be 2 0 1 0 minus 2 and 1, and this one you will obtain as 3 by 2 half 0 1. So, this is 0 1 3 by 2 and minus half. So, now calculate the Zj minus Cj using the normal formula, you will obtain 0 0 0 0 and 1. Now, in this case your Zj minus Cj is greater than equals 0 for all j. So, what we are finding now in this case, Zj minus Cj is greater than equals 0, and if you see the basis, the variables are x 2 and x 3. No artificial variable x 5 is present in the basis. So, therefore, we must obtain some solution for this, and we will go to the phase 2. In the phase 2, again we will start with this table only, with the earlier table only, that is with this table. The only problem will be in this case is this Cj values will be replaced by the original coefficients of the variables x 1, x 2, x 3, x 4. And also you see in the last table of phase 1, this variable x 5 is not present in the basis. Therefore, x 5 will be removed, this column will be removed from the basis, as we have discussed in the algorithm. So, that you will obtain your x 2 and x 3. These values now will be 2 1 3 0 if you see the original problem. sorry, this will be B is A2 A3, this will be X2 X3. So, CB values will be 1 and 3. I am writing these 2 0 1 0 minus 2. This will be Zj minus Cj. So, sorry, this is 2, this will be 3 by 2, half 0 1 3 by 2, whatever was there in the earlier table. If I now calculate Zj minus Cj, I will find that it is coming 5 by 2. Zj minus Cj less than 0, 1 negative is there. So, your entering vector will be x 1. So, since the entering vector is x 1, so calculate the ratio by b by x b. This is 2 by 0. So, you will not get infinite value, and for this case it is 3. Since only one number is there, so outgoing vector will be now x 3, and this will be your pivot element. So, that x 3 will be replaced by x 1 now. So, this is a 2 a 1, your Cj values are remaining same. So, here it will be 1 2. So, this I will make 1, this is 0 already. So, the table you will obtain 0 1 0 2, and in this case it will be 3 1 0 2 and 3. Zj minus Cj, if you calculate 0 0 0 4. So, your Zj minus Cj is greater than equals 0 for all j. So, we obtained the optimal solution, and the optimal solution is unique, because Zj minus Cj equals 0 for basic variables x 1 x 2, and it is greater than 0 for the greater than equals 0 for the non basic variables. So, optimal solution in this case you will obtain as x 1 equals 3 from here, x 2 equals 2, and your x 3 is not present here. So, value of x 3 will be 0 and z max will be 8. So, this is the optimal solution, unique optimal solution of this particular problem. So, I hope the method is clear. In the next class, we will discuss two different problems on this two phase method.